Thanks all for coming back. I hope you all Googled how to save the vaquita. And next one. And yeah, here it is again. So yeah, now it's like I have post-quantum. I mean, this is the motivation, but we're not going to talk about anything quantum. We just assume that D log is no longer hard, so we need something new. And yeah, the problem is that, like in the proof that we saw before, if the discrete logarithm is no longer hard, we have no more soundness. Yeah, if you remember, because then it would be easy. We had this commitment that is compressing, but if the discrete logarithm is not hard anymore, then the prover can just change what he committed to in the first round, like any and also the commitment, it's just no longer binding. And yeah, and here, because I said it also in the first talk, we had succinctness. Here we focus on soundness and zero knowledge. We're not going to talk about succinctness, but they can also, what we're talking about today. You can also put the compression on top, but then you have new challenges that I'm like maybe talk about a little bit. But yeah, you will see that getting the Sigma protocols for lattices, it's much harder than the discrete log, and then yeah, everything you want to do on top even more.
Yes. So your protocol was kind of generic for any homomorphic commitment scheme.
Yes.
But it's kind of still not easy to build that kind of homomorphic commitment scheme from post-quantum secure assumptions.
Yeah, you will see it. We will do that. Yes, in the talk we'll get clear what the issues are. Yeah, in some sense that's the hope, right? That we just put it in, plug it in. But yeah, yeah, and the application, just talk about, we already saw this post-quantum signatures, and this also gives you post-quantum signatures, and I just want to give like a very short idea. So here on the right, this is the form of a Sigma protocol. If you remember, and I think we have not seen this, but maybe you've seen this already this week, so then you see it again. How do we get, if we have such a Sigma protocol, how do we get to a signature scheme? So the idea is that now the prover becomes the signer, and the prover still can choose like a witness in the statement, such that from the statement it's hard to get the witness, and then the public key will be this X. And something that the prover knows and no one else is this witness. So this will be the secret key. And then the idea is to sign a message. We can kind of like run this Sigma protocol, but using random oracles. These you have seen on the first day. And so I commit, like I choose the first round message honestly as the signer, and then I can compute the challenge. And instead of getting the challenge from some verifier in a signature scheme, we don't have a verifier. We just want to do something non-interactively. We compute the challenge as a hash of the public key that we have of the first round message A. This is important. Why is this important that the first round message A is in here in the hash? Yes.
We know that we can, if we do it in the other order as the prover and first select these values, we can. So basically, we need to make sure that the prover cannot predict when the A has to be fixed first, and then.
Exactly. Very good, thanks. So the issue is, yeah, because if we have this honest verifier zero knowledge, so if we allow to choose the first round message after the challenge, we can basically simulate it. And here H is modeled as a random oracle that was briefly discussed, so we have to kind of assume that the output C is random. Yeah.
This might be a more real world concern, but also wouldn't including A be important to have a notion of context binding?
Yeah, so this is also why you want to include the public key, and depending on your setting, maybe other things. But like here, it's even worse. If you don't include A, everyone can forge the signature. So it's not just like, it's just completely like yeah, not a signature scheme anymore. Yeah, and then you can compute the third round message, and then the signature can be just the first round message and the last round message, and then the challenge can be computed from those, and then can be checked if really this protocol would verify. And the intuition is, if I'm able to produce such a signature, I can do here. If I'm able to produce such a signature, then I really must, because this challenge I cannot predict, so I really must know this witness W. So only the signer can do it. Yeah. And yeah, so this gives post-quantum signatures. And there's many more that follow this like the original blueprint or the Schnorr signatures, and yeah, now there's many that use the same idea. So basically, Sigma protocol directly gives you signatures. Okay, so now we have Sigma protocols. Again, another like the slide appears many times in the talk. So we have completeness. We need 2 special soundness. Now we're back to 2 special soundness for the rest of the talk. And now important honest verifier knowledge. So honest transcript can be efficiently simulated without knowing the witness stuff. Yes?
A question we discussed in the break. Would you have less security somehow if you had 3 special soundness instead of 2?
So you have you get a larger knowledge arrow. So like the knowledge area is 2 divided by the size of the challenge space, because you could know 2 challenges and still not know the witness instead of 3. So this doesn't look like such a big issue, but then if other things like it doesn't compose as nicely anymore, like parallel repetition, if you have 2 special soundness, it's much nicer than if you have 3 special soundness. There is a slide on the slide deck on the last slide that there's some more information. Yes.
And then when you had this 2, 3, 3, 3, 3, and how do you compute then the soundness error or like?
So the soundness error. This is so the soundness error there was like log n divided by p, something like that. 2 log n divided by p. And so this is like there is a kind of like this is not. This is actually non-trivial, and this is something that we did when constructing Sigma protocols from lattices, because there is much more important because things are harder. There you get actually like there you can show that if you satisfy 2, 3, 3, 3 special soundness, or more generally K1, K2 up to K5 special soundness, you get a knowledge extractor with some error. That's like there is a formula that you just plug it in. So it's very nice because the knowledge extractors are usually much harder to give. But with Sigma protocols, you just need to prove this kind of special soundness, and then you're good. And that already gives you the knowledge error. But yeah, the knowledge error gets larger if the kind of the more challenged. Other questions? No, good. And yeah. Maybe just like why is honest verifier serial knowledge enough for the example that we just had, that we just discussed? Why is it fine that we don't have general serial knowledge?
Random oracle is honest.
Yes. Yes, we assume this perfect random oracle that's also honest. No, but yeah, so this is not an issue. Yes, and when we construct them, this was also the first kind of question or remark. We already have a blueprint, right? So the only thing that we need is, in some sense, hopefully, to instantiate this. Yeah, everyone still happy with that? Should get bored by the slide by the end of the talk. So yeah, so that we just have to instantiate the commitment scheme from a new assumption. So we need a new assumption, and the new assumption, yeah, this one are the homomorphic commitments. We already seen that before. We need it to be homomorphic. And succinct, now we don't care anymore. Like actually, we will get some kind of succinctness, but we're not going to talk about it much because we just care about your knowledge and sound. And the assumption that we're going to work with is this assumption, the short integer solution. And it states that, and I'm also going to put the picture. So it states that we have this big public matrix here. And it states that it's hard to find an S such that this is 0, and the important part is it's hard to find a short. Yeah, I'm not good with this. A short S in the sense. So you can consider different norms here for simplicity. Let's just consider the infinity norm. So just the maximum entry of all this. If we just view set Q as integers between minus Q half up to Q half, and then just take the absolute value of this. And then obviously this is easy, but this is very important. This is easy to solve if I don't have this requirement, right? What can I do?
Gaussian elimination.
Yeah, a Gaussian elimination. And this is really, really, really underdetermined, like the way people set it up. So this is a very long one. And so there will be many solutions, and it's very easy to find. Okay, and so the hard part is to find a solution that is short.
Why is it not called a small integer? Problem.
Yeah, the shortest can mean different things, yeah.
Is that the infinity norm? It's like small, right?
Yeah, I guess if you use the L2 norm, you think more of a short vector. Yeah, I'm not the person to ask. I was for a moment, I was like, but it's a short integer solution, right? It's not small integer solution. No. Yeah. Okay, good. And yeah, and this is just a side note, but this we don't even if we had this full powerful quantum computer that would break out discrete log, we don't know how to break this assumption. And so this is something where we can hope to get something even. Questions to this assumption? Yes.
What is B?
This is some bound that we have to set, and like the larger the bound is, the easier the problem becomes. So obviously, if B equals to Q, then this is very easy. And yeah, if B equals, I don't know, say 1, then this is like the hardest we can get. Yeah, we need it to be at least 1 because we want a non-zero solution. Zero solution is of course also easy to find.
But in practice, is it like very like on the order of 1?
It's quite, it depends on the setting, but it's quite small, yeah. And we will also see later, yeah, we will see later, like for what we're doing, it cannot be, we need hardness if it's not actually bigger than that, for another reason. So this will maybe be answered. So it depends, but much smaller than. So you can even have the large one and then just choose Q even larger. Yes, and then yeah, there's ways to find out parameters that make this work. And just to look now, because that actually, like what we have looks quite similar from what we've already seen in the last talk. Here on the like discrete logarithm, we have a group with a generator and the order, and now I changed notation slightly to be like consistent with this talk. And here we have the W is a witness, and we can also extend that to long W's, right, with the vector commitment schemes. And here our W looks like this minus beta to M. And yeah, the statement is G to the W, and here the statement is X equals A times W. And we also have, this is already important, so here we have this homomorphic properties, and here we also have that. Yeah. Because A times this, just because it's just a linear operation. So we can both do like a scalar multiplication, we can add 2 up. So we get kind of the same thing. Yeah. Questions? Yes?
Yeah, is beta here connected to B from the previous slide?
Yeah. I gave it a different name because oh yeah, no, it should be B actually, sorry. Yeah, there's a beta and there's a B later, and I wanted to, sorry. So yeah, now for now you can think of, later it will be a little bit smaller than the cis assumption, but since we just have cis assumption here, you can for now think about this beta to be the B. Good question. Thank you. Other questions? This is important, so if any questions, no, later, you can also ask me later.
Just clarifying question, will X be 0 here from the cis assumption?
So yeah, later, so for the cis assumption, it will be 0, but kind of the kind of, if we use it as a commitment, maybe the slide was a bit earlier, it can also be that that's not like this later, this X, like here, this X was a commitment to W, later this X will be a commitment to W. And then like you can show here that you can solve discrete logarithm if you can find the witness. Here you can show that you can break cis if you can break the binding of the binding. Yeah, like as I said, I'm like thinking about it. This slide was a bit too early.
By the commitment schemes, hardness then relies on ICIS, so inhomogeneous cis, or is it reduced to the cis?
It's reduced to the cis, and we will do that later. I just put this slide too early. So that will come up again. Yes. Yes.
Sorry, what is the set that the witness is included in? Like, what does it mean to the power of M of the set?
What this one here is the question. So basically just all vectors of dimension m where the infinity norm is less or equal to b.
Oh, yeah.
So just all the short vectors, we're gonna call it short vectors, so just a short vector. Yeah, so this is the difference, and this is actually the difference that makes everything more difficult, is that here this thing is short and this doesn't have to be short. Yes,
What are the characteristic of the matrix? Can it be anything?
and this will be a random, this will be chosen at random usually. Like we assume for the rest of the talk will be chosen at random, then maybe you want to do different things to get it more efficient, but for now just think of a random matrix.
M is a public value, I guess.
Everything is public here except for this, for the weakness. The M is the K, the A is also public. Good. Other questions? Great, thanks for. So yeah, homomorphic commitments, so now actually we define it. So how can I commit to value? Well, I just exactly do this thing. My commitment will be this vector W times the matrix. And yeah, this has to be, and now this has to be small, right? So for example, we can no longer think of this as a vector in set Q to the M, but we can think of it, for example, in binary representation. So is it hiding? Is this hiding?
Yes.
I feel like both. It's somewhat hiding. Yeah, as before, to make it fully hiding, we need to add like here some randomness.
Why is it called MSys now? Was it MSys before?
Yeah, because I changed it's cis, and then we will later generalize to MSys. So all the MSys that you see now should be cis. Think of cis for now. MSys is just a generalization too.
Sorry, why do we have to think of it in binary representation now?
We don't have to do in binary representation, but it's important that W is small, because if it's not small, then the problem is not hard. This is not hard.
It's been binary vector.
Yeah, as a binary vector, so something like 1, 0, 1, 0, 1. So just think of this W to have something that has small norm. In the rest of the talk, it will just have norm smaller than beta, and then however we want to, just not think.
I thought you mean we have to change the representation of.
No, sorry, that's a bad phrase.
Okay.
Just think of this as a.
Yeah, it's
vector
short,
with
it's
small-
just
short. It's a short vector. Yes. Yeah, and here I use also small to make. Yeah, it's short. Yes.
How do we enforce this? That it's short?
And like when you open, you can check, right? If you open later a commitment, then you will only accept kind of this as a valid commitment if it's really short. But of course, otherwise you cannot enforce like how someone forms the commitment, you don't know. But like later, if you open it, yeah.
Can you give an intuition why you need to basically pad some randomness at the end of the witness? Because from what I see, it's like, it's an underdetermined system of
It's
equations.
underdetermined, so you will for sure not get the W, but you get some information of W. So to be like fully in the sense that if you wanted to be fully hiding, like information theoretically hiding, you add some randomness and then the rest is fully hidden. But like you have some hiding. It's similar as for the discrete logarithm also. If you don't add randomness, you're hiding, but you're not fully hiding because you can check if a certain linear combination is possible or not. Or if a certain vector W is possible or not. But as soon as you add randomness, you get fully.
But I guess Elena's point is that it's not like in the discrete log setting, no? Like what she's.
Yeah, so like there is more than one solution, and I can never determine which is the exact solution.
Somewhat hiding already.
Yeah, it's like in the discrete section and for the vector. Yes. Sorry, yes, but that's a very good point. Thanks. Like for the vector commitments, we have, because it's compressing, and this is also compressing, we have some hiding, but not. Thanks. Many good questions. Yes, and binding, is it binding? Yes, it's binding. Otherwise we would not define it as a commitment scheme. So what happens if I have two of these commitments which are the same? What can I do? But I assume that the W's are not the same. Yes.
Subtract from each other.
Yes. So I subtracted 2, and then I will get 0. Right. And so if I assume, so that answers your question from before, if I would assume that these two are less than beta, and that maybe also clarifies the beta and the B maybe, then I know that if I subtracted 2, then I get 2 beta. So if S cis is hard with this b equals 2 beta, then I have, then I'm finding, yes?
Probably a dumb question, but what are the two lines?
Which lines are?
Vertical lines around.
Oh, this is the absolute value. This is the norm where we take the infinity norm. So I just look at the biggest entry. So I have many entries here. Just look at like the largest entry of this, and I assume all the entries here are between minus beta and beta.
So is it the largest entry or the absolute value?
The absolute value of the largest entry. The largest absolute value of an entry. Sorry.
Largest absolute value of an entry.
Yes. Yes, I take the absolute values of all the entries and then I take the largest of this. Yes?
You know, maybe it makes sense that you called it beta before, because now B is 2 times beta.
Yeah, exactly. But I had the slide too early. Yes. Good. Clear? Good. Is it homomorphic? Yes, we already had the slide that shows that it's homomorphic. And it's even succinct. Right? That was your question already, like depending on the parameters that we choose, but kind of the way the size we can choose it, this actually to be much smaller than m. Of course, the longer we choose it, it changes the assumption, the easier the assumption gets. So it changes the parameters. But yeah, but we can still get it hard, like a hardness, even if this vector is very long.
Can it be log beta to now?
Yeah, it should be log beta. It's small anyways. Yes.
Yeah, regarding the hiding, how much randomness do you need to add to get perfect hiding?
To get perfect hiding, like that you have the output dimension is k. You're like k q, so kind of k log q.
Okay.
That's the entropy.
Probably will say it in the slide too, but the homomorphism is like almost because you get the blow up.
Yeah. So I should have not done I should have done this like also orange. That's also another issue that we have here. Yeah, because of this small. That's a very good point. Yeah, if I add 2, then instead of beta, I will have 2 beta. Anything else? Any other questions? No. When did we start? Oh, wow. Sorry, I'm not gonna finish earlier. Okay, so now we have that's very good. So hopefully everything is very clear. Now we want to do Sigma protocols, right? We have a new commitment scheme and we have a generic scheme, so we can just plug it in, right? So this is just a scheme from before. Do we get completeness here? Does this fine? Like, does the verifier accept if I really know the witness here, and then I send random, and then I check this equation? Yeah, I see a lot of nodding, so I have completeness. Do I have zero knowledge? Is this the set that I send here with the R plus C times W is hiding? Yeah, I see some nodding. Yeah, it will be hiding because this R is like a general set Q element, and so this fully blinds my witness. Is it special sound? I see some nodding and some no.
Why not?
Bound is small, the set bound is smaller.
Yeah, so that's exactly that. We have an issue here because we didn't check anything on the bound of set, right? And so yeah, well, the prover can now choose arbitrary W, and the verifier will still accept, right? Because it will just check if this is and this is an easy task. We just said in the first I can just find such a W. So now I didn't prove anything. Like I proved that I know an opening, but not a valid opening. And I want to know that I know like valid opening is just if also W is. So what can we do? It's not good. Well, we can check something here. We can check if this set is small. Is that good? Oh, it's not good. Why it's not good?
Because R is big.
Yes. So even if we start with a small W, then the verifier will not.
We have R small.
Yes. So still not complete. So let's choose R to be small. Are we complete now? I still have a no, no.
We still not. We need to verify still not.
Yeah, we'll talk about this in a moment. Let's just first, are we complete? Like we first need to get a complete protocol.
Need to check.
You should check 2B maybe.
So no.
And so the thing is, we still have this challenge here, right?
Oh.
Okay, so we still, even if we check 2B, but this will be the next thing. So still not complete. Well, okay, let's try, let's be happy with a small challenge space. And then do what you suggested, Carla. That's okay. Let's do beta. So are we complete? Yes. Are we honest verifiers, zero knowledge? We have zero knowledge too.
Sorry.
Yeah.
Can you explain why the previous attempt wasn't complete? I kind of missed it.
Yes. This one, it's not complete. It's good that you ask. Thanks. It's not complete because that C will be a general set Q element. And so I blow up, like I have this W is small, but then C times W will not be small anymore. That will just have the norm will be basically C times, can be up to C times the norm of
Then the
W.
check fails.
Sorry?
The bound check fails. Then
And then I will check the set here, and then I will not accept even if my W was small to begin with. Yes, thanks. That's very important. Other question, is it clear?
Surprisingly.
Very glad to hear that. Yes, so okay, so now we have this and we have this check, right? So we say, okay, just here one, and then this is beta and this is beta. So if I add the two up and like, or just have one, then we're less than 2 beta, right? So this is like complete, we're happy. Are we zero knowledge? No, why are we not zero knowledge?
Well, something on the distribution of W by repeating that.
Yes, exactly, because now R does not hide W anymore. Because for example, if I see that some entry is 2W, then I must know that VI was W. I mean, this is like an extreme example, but obviously like we shift this distribution exactly by W. So that actually leaks a lot about W. Okay, and so what is the issue? What issue do we have here? Why things are not so nice with lattices than they are in the discrete logs?
Modulo? Yeah, there's no modulus.
Sorry?
We compute in the integers and we don't.
We have the modulus Q, like we don't even have that, but we have this.
Not big enough. Yeah.
We have the smallness. The smallness that's not the same as the modulus. Yeah.
Yeah, we propose with distributions, like we need to somehow, we kind of need two different distributions in a way and find meet somehow in the middle. Like, you want it to be like uniform or like a large set but also we need to keep it short, the vector short, and yeah.
Yeah, so exactly like you say, we want this to be large to get zero knowledge. So we want a large distribution, but we want it small for soundness. Because, right, if I just now choose this bound to be like, if I remove this bound again, then I don't have soundness anymore. So we have this trade-off. So what do we do? How do we get both? And so there's two options, or actually it's just maybe two viewpoints of the same option. Well, we can choose very large parameters, exactly like you said, right? We can choose like a very, very, very large V here that just hides this beta because it's so large, because the probability that I like this distribution just completely drowns this distribution of the witness. And then I have to choose an even larger modulus that I still have some hope of cis to hold, that I also get soundness. And then do we have, if we do that, do we have zero knowledge? Yeah, I mean, the thing is that set would only reveal something if I get above this bound, and this only happens with very small probability just because I choose those. And do we have soundness? Like we have this two, right? So we have one with challenge 0 and like we have one with challenge y. So we have set and set prime that open relative to the same R. And then I can just subtract it, right? I can just subtract this C, this is just R from C prime. And then I get that this is a valid opening for W with this norm 2B.
So it would become some form of statistical honest verifies your knowledge.
Yeah, this is statistical honest verifies your knowledge. Yeah, and then we have two special soundness, and this is hard to find. Like this gives something this gives something meaningful as long as this 2B is still small enough for sorry.
Two beta or two?
No, this is 2B, right? Because we have the R here at least one time. So maybe it's B plus 2 beta or something like that. Maybe I over did the count a little bit here.
If your soundness is a little bit.
Then it's an R prime or something?
So the like I.
So otherwise the R cancels out and Z prime minus Z.
Yeah, this is
But the bound in the C and Z prime is only up to B.
Yeah, no, so actually, yeah, we get 2B now. I like the set prime and the set prime and the set, we're not guaranteed to get really the witness. The prover can do whatever he wants. We just know that these are both binded by B because otherwise we reject and then we get 2B. Thanks. Very good question. No, you get actually 2B because you know that this is set prime has norm less than B and the set also has norm less than B. But you don't know this first thing like this. Like you don't know anything if this is really like if you don't know anything about this. No, this should be the same witness, but you don't know anything about like what they actually are. You don't have a guarantee that you actually get the witness.
And it's not perfectly complete anymore, right? Because you could go over B.
So it's perfectly complete because we only abort if we have 2B.
I see. Okay.
Yeah, we only abort. So this is I only define it on the next slide. So we're perfectly complete, but we have the soundness gap, right? We start with something that's very small, but we can only extract something that's actually quite large, much larger than the first one.
Here the norm bound is 2B just because it's the binary challenge. Challenge larger, you get more.
Yes, that we will also do. Yes,
Okay.
yes.
Just checking, there's supposed to be a parentheses between R plus 0, like, no, or
R plus 0 times W. What do you mean?
R plus 0 should be in parentheses or not?
No, this is just this is like the
0
first.
times W?
This is just R basically. So this just cancels out. I just read like, so this is just R. We know that if the challenge was 0, then I get back an opening for the first round message. And if it was 1, I get back an opening for R plus the first round message plus the witness, and I can just subtract it to this was and this should also be this is a very bad way to write it, sorry. And then you really just get an opening for W just by subtracting.
Maybe I should wait for the last slide, but if we check that set is smaller than 2B, wouldn't set prime minus set then be smaller than 4B?
No, we check that it's smaller than B. Oh no, you're right. Okay, no, sorry, we have a small completeness error. We will fix that because we will set it up a bit differently. But we will do it. That's a good point. Yes, thank you. Yes. And the option 2, so like here we have this observation that set only reveals something if this is larger than B. Otherwise we're fine. Right? Because we will also have an image in the next slide. But the idea is actually we can also choose a smaller bound B. It doesn't have to be this big, and only send out set if it's fine, if it doesn't leak anything. So this is kind of like also called rejection sampling. And this is like we just talk about uniform rejection sampling. You can also do it with Gaussian distributions, but we just talk about uniform rejection sampling. Yeah, and I will just skip over this and go to the protocol first. Because now the protocol, how it will look like, is because we already talked about it and we haven't really defined how it looked like. So now we choose this R from this larger distribution to have 0 knowledge. And then, and to make sure that we really have zero knowledge, if this would be larger than B, then we abort and we go back to and we resample R. And in here, we check if this set is smaller than B, and if it is, and this equation is also satisfied, then we're happy. Yeah. And intuitively, like what we have showed on the slide, we will also go through it again in a moment. Intuitively, what we showed is like now actually we get zero knowledge, just because we always abort if we would leak something, and we also get soundness if we say it's hard to find a solution that's of size 2b. So then we will still get soundness because we can extract but we have the soundness gap. We have to start with a small witness here, and we only get to extract something much larger. Yeah. And then how does this rejection sampling look at? So just to clarify when we have to abort or why we have to abort. So we have this here, we have our witness, and it can be anywhere in this small square. Now we're just two-dimensional, right? So say this is 1, and we know that our witness has only coordinates smaller than 1, so we're somewhere here on this small square. And the potential image, it depends on the W, could be anywhere in this big square, right? Because we start here, and then we can potentially add something that's of size B. Yeah. And so if we start with a specific witness, which we will do, then all the witnesses that we will get, they will be in this orange square, right? Because I start here, and then I can go B from any of these points here. So this is the possible image of set if this is this specific witness that we have. So here it's beta, like 1, 1, for example. Yeah. And then what do we have to do? Well, now that what is not safe, like when can we not give it out? Maybe I already said it.
Top right corner.
Yes, exactly. It's like this top right corner, because we would never reach this corner if we would here, so we leak something. So, but if we're in this square, then we're safe to reveal it because that we could reach from anywhere. And the abort, like the probability that we abort is then like 1 minus, and this like this the small divided by this where we could land, divided by the big one. And just to kind of like, if we have if we would choose B approximate beta, it's not a good idea because then our abort probability would be negligibly close to 1. So would essentially always abort. But we could choose very small parameters. We can just never get something out. And if we choose B, this super polynomial, then our abort probability is 0. But we get very large parameters. So what we do is like something in between in practice. Yeah. Yes.
I have a quick question. Can you go back to the signal?
That's not good if you have a question.
Sorry, I didn't know that. Or maybe like the one after which is something.
This one, the one after, yeah.
Yeah, with the probable. Right. So if the normal set is equal to to B.
Yes.
Then it's less likely that. And so if Z is equal to B, then is it like also some corner case where you can deduce something about?
I don't think so, because you can get it from everywhere. But
so say C is equal to 1, right?
Yeah, but then like the probability that you get anything that you can reach is the same, right? If you abort, if you cut off the corner. We can discuss it in the break, and then you can.
Yeah, I think you cut off more if the witness is to the edge of the.
Okay, maybe you have to cut off a little bit more. Like it could be. Let's so you have to be careful with that, but like in principle, that should work. Like the corner case, I'm not 100% sure now. Intuitively, it did make sense to me that it's fine, but I would not.
Yeah, usually you cut off so that it doesn't make any difference. So even if your vector is all B's, you always cut off that you always get like it's that you have the same rejection rate. Otherwise, you would have side channel information about this.
Yeah, but yeah, so let's say like there's a way to cut it off that's very close to B, either exactly or smaller that this works. Yes, so we have this protocol here. Yes, so we're complete. Are there other questions, or are you happy somewhat with the?
I think now it's perfectly complete. Just might run a long time. Yeah.
Yes, exactly. It might run a very long time, but like that. So we have honest verifier serial knowledge with abort, like in the sense that if we don't abort, then this doesn't leak anything.
But if you do, then it might.
If you do, then it might, yeah, but it's fine for us because if you use it in the Fiat Shamir setting, you will never reveal it if you abort. But if you really want to use it as an interactive protocol, you have to be a bit more careful, yes, because there it does like leak something.
So where do you abort? Like I thought you repeat, but maybe.
You like but like if you really run it as an interactive protocol, you always have to send the first message and then you get a challenge. And yeah, so you can for example also commit to this first message instead of just sending this message and then only reveal it. But then like for now we're happy with, like we say, it doesn't reveal anything if we don't abort.
So just to check if I understood the point, if your witness is like all betas, then you have a higher chance of aborting. And if no?
It's the same, you just move the square.
Right. So why do you leak something if?
Oh, just because like technically this does leak something about like we don't have like this does leak something. It's a commitment, but this is not like, since we consider the whole thing, it leaks a little bit about this what is committed in here.
Right. Okay.
Not a lot. So the question is how much you can, but it does leak a little bit. So you have to be more careful to say like you do leak a little bit about R.
That makes sense.
Yes. Even if this whole envelope thing leaks something, it leaks the randomly chosen R. It doesn't reveal anything about the witness, so I think it's fine.
It does reveal something about the witness because whether you abort or not depends on R plus the witness.
Yes, if you don't send the R, set is fine.
So the abort does depend on the witness. So whether you abort or not, like if you would know R and you would see if you abort or not, and after some iterations you would, and you don't send R in the clear, you just send a commitment, but it still carries some information about R. So this is just to be fully.
And does it not like just affect how often you abort? Does it not spoil also something about W? Because if it's like the all beta vector, then I'm more likely to get out of the squares than if I'm just staying in the middle. Like if it's a zero vector, I would never abort.
Yeah. So we just say it's like if I just run it and you don't abort it. So like if you run it, like if you use it non-interactively.
Okay, non-interactively. Okay, I don't know how.
So we just care about it. This is the honest. Yeah. Okay. So we just assume that this is not an issue. We don't care. Like we don't deal with this issue. And otherwise you have to do something. Yeah, I'm not sure. Like but otherwise you could also do something to make it work, but then you have to work a little bit harder. Not much, but a little bit.
You can maybe just not have perfect completeness.
Yeah, but the issue is really just you have to do something else because once you send it and then whether you abort or not might leak something off the W. So this is really just about honest verifier serial knowledge. That's something you can also not simulate because you don't know what the actual witness is. But this is like a super small detail, so it's not so important. It's not something that we need.
The main goal is to build signatures, right?
Yes, now we build signatures and then this is fine. And even if you don't build signatures, you usually want to use it in the non-interactive. Yes?
Just a stupid question. Because you're giving up so much now, you're giving up the large talent space and you're giving up the fact that you don't that you need rejection sampling and so on. Is there like a way? Have people thought about proving that I've committed to like a vector with very low norm? Is there some way of doing that? somehow differently?
Like in a different way. Yeah, I mean, you can use other ways to do this, but like we get a little bit, like we get better than that. Like this is just, so we will talk a little bit about extending the challenge space and then getting something else. And yeah, Khan will also tell more about that. But yeah, like this is, it's just like to show that, yeah, with the small norm, the sigma protocols are not. Other questions? Yeah, and we're special sound we can extract, like we said in the slide before, but with some sound escape. And is this like, this is maybe already follow up on your question, like this is not, I mean, the sound escape is not great, but there is a sound escape. We cannot get rid completely of the sound escape if we do it like this. But the challenge space is also really, it's also bad, right?
What do you mean with the sound escape? That the two
what
bits higher? Or?
That what I extract is larger than what I have to start with. So it's not a special soundness in the sense, usually you say, oh, I can extract the witness that's in the language. I start from some language and I can extract the witness from the language, and here starts some language, and then I extract the witness from a larger language.
Larger language, yeah.
And so there I have this gap. And yeah, I cannot start with this. And this is also an issue that if you now go to compressed sigma protocols where you have many rounds, then then you get even like larger and larger and larger and larger. So this makes also things more difficult.
So what is soundness gap in practice? Does that mean essentially that, okay, you have soundness reducing to a slightly easier problem, and so you need to increase your parameters?
Yes, exactly.
Right.
We would have to amplify soundness here, or I'm just wondering what happens if the prover just guesses the value of C.
Yeah, no, so this is certainly not good, right? If you just run it once, then with probability 1/2, the prover can cheat. So this is not good. So this is the next slide, so it's very good. The prover can cheat with probability 1/2. And yeah, so like, of course, we can like do other things like, I'll talk about it, and you can repeat the protocol, but what about if we choose it, like we need the challenges to be small that we already found out, but what about if we extend the challenge space a little bit? Is that good?
Blows up the norm of the response.
Yeah, how much does it blows up the norm?
I don't know which norm you use, but by delta.
It's actually worse than that. So that it does blow up the norm, and it's even worse than that. And that's why I want to point it out. Even if I just add -1, what happens is that like I have -1 and +1 potentially. And then what I can extract is that this is a valid opening for W, 2 to the -1, because I get the witness 2 times. And now 2 to the -1, even like the 2 small, 2 to the -1 will be large in general. So even I just added one more challenge, and I cannot extract a short solution anymore. But this is really to show that, yeah, that this is difficult. Yes?
But then can't you just choose your challenges in such a way that their inverses are small?
Yeah, so not in, if you, this is also something, but like we will go to a larger ring, and then you can choose more challenges. And what you can also do, yeah, this is the problem. We can also, there's also something else that is done, that we relax to approximate proofs. And we say, okay, we just say, I want to find that small w and small gamma, that a times w is gamma times x, and this will still be like, then here I will have the 2, gamma equals 2, and this will still be a hard problem for the right parameters.
Not implied by this.
No, it's a different assumption. And yeah, and yeah, even if we do that, then this is still small, and now we only have approximate proof, so it's not great. And this is important for next talk, I heard, so pay attention. If I have 2 approximate openings, A times S0, gamma 0. So if I were to extract like two valid openings, so just to say that the prover has a little bit less freedom than you might think, then we get that if I subtract the 2, if I take S0, then this will be 0. So S0, the vector, the solution I extracted times gamma 1 minus S1 times gamma 0. So that means either these fractions are the same. So either I extracted kind of the same fraction, so the prover is committed to the fraction, or I'm back to solving the cis solution. Yeah.
So what's the fraction here?
The fraction, like kind of the S. 0 times y gamma 1 is the same as S1 times gamma 0, or S0 divided by gamma 1 is the same as S1 divided by gamma 1. So just this is something to remember for the next talk. Kind of that the prover is a little bit like, so the prover could not, it's not able to solve cis, could not kind of come up with a different one each time. It's not so relevant for what we're talking about now.
So are you saying that this is implied by cis now, or?
No, but if you could find two different ones, then it would be implied by cis. Either you're kind of bound by the fraction, but if you find two different ones, then it would be applied by cis. So it's not necessarily hard to find, like cis does not imply that it's hard to find W gamma to do it, but cis implies that it's hard to find W and gamma 0 and W and gamma 1, that where the fraction is different to find it. Yeah, is that good for your talk? If you can come back in the break and look at it for the next talk if you still have a question. Yeah, and this is also important for the next talk. So we're preparing already. Yeah, I'm not going to give you any time. Sorry. So like what we can do, like, so still it's limited, right? Because still, even if I do this, then this delta still has to be small. Like this already blows up. So if I choose this now, it's exactly like you said. I blow up this norm of gamma and W exactly by this delta that I have here, or the norm of this gamma it flows by. And so what we do, we extend the challenge space. So we go to the ring RQ. Where we just take ZQX and factor out. And so now our elements will look like this. So we will have polynomials up to degree d-1. And this is something that you will also need for the next talk. So just to write, because we factor out x to the d plus 1 here, we will have that x to the d minus 1. So if we add two of these values, then the norm will not blow up much. Like here, what I consider, this is actually very important. So here I just take the norm to be the absolute value of the largest coefficient. And so like the absolute value of the largest coefficient will be smaller than I just add the two individually. And if I multiply, it will look like that. So basically I just take all the coefficients where j and k adds up exactly to I, and then because x to the d is minus 1, I subtract the one that add up exactly to I plus n. Yeah? And then, so what does it mean for the norm? Well, this norm is less than a plus b, and this product is less than d times a times b. So it blows up, but not too badly. Yeah?
You get a factor of 2 there?
Should there? Is it not just adding this up, d times a times b?
Twice, right? AJBK. Oh, I see there. Yeah, I mean, AJBK, everything there could be as high as the norm.
Yeah, but then you have the a and the b norm. So maybe there's a factor 2. I'm very bad at staring at the slides when I'm standing in front. Yeah, so big O of like some modulo something.
What is the difference now from before? Like, how is this better? How the norms blow up?
Yeah, so this is better because now we have more elements that have a small norm. Before, the only elements with norm 1 was like 1 and minus 1. Yeah, and now we have many elements with norm 1. Namely, we have actually 2 to the d elements with norm 1. So we just have more small elements, and that's excellent question, and that's what we want. Yeah, and so we just extended our space of small elements. That's all we wanted to do. Other questions? If this is not clear, come back in the break and look at the slide for the next talk.
What norm is defined here?
So we just take again the infinity norm over the whole, and then for like if we just look at a single element, just the largest the coefficient, like coefficient norm, just the largest coefficient of one of the polynomials. Is this also what you
coefficients? Yeah.
Yeah, coefficient norm. And now we have a new assumption. So now the assumption is, so here it's also again stated the norm. Now the assumption is the MSIS assumption, which already showed up before, where we do the same thing, but like over this larger ring. So my secret is now from RQM, and we still want this to be small, and my matrix is also from this larger ring. Yeah, and then now we have more flexibility with the challenge space. But yeah, challenge differs are not necessarily invertible anymore. So if we want exact proofs, we have to be careful that our challenge if they are really invertible, because otherwise we cannot extract anything at all. But for approximate proofs, we just need that these are small. So we get now we get a large challenge space by just taking all the C's of all the C's, like it's not even of norm one, just binary, for example. And then if D is large enough, we now have an exponential challenge space, just because we have more elements.
What if you use the field extension rather than the way?
I don't know.
You want to make sure that the product of short elements is still short.
Yes. So that's the important part. So we need to do something. That's the crucial part. Yeah, we need.
Not clear, I think, how to define a norm in that case.
I've thought in the same way, but yeah. But maybe then it's not that useful. Yeah. That's
Fire alarm. It's fire alarm.
Yeah.
This is I should be. This is my last slide. I think that's not bad.
Loading.
So you can look at it while listening to this beautiful sound. So yeah, if you're just interested in signature or identification schemes, then this is actually good enough. So this is what we see today, because if this is still a hard problem, then this still gives you something interesting, and then you can actually get small proof sizes, just because you have this, you can do this tricks, like choosing the larger challenge space, but in some settings you will need exact proofs. So yeah, that I didn't say actually. So thanks to Khan, like I put you on the slide here, but it's much like many of the slides, not only that I give credit to, are actually based on Khan's slides. So yeah, I didn't want to just steal them, which I also sometimes do, and then don't give credit. So credit. Yeah, that's it, I think.